Okay, welcome everyone to the 2017 AFA lecture. I'm David Sharfstein, and it's my great pleasure to introduce Sendhil Mullainathan. Sendhil is the Robert Wagner Professor of Economics at Harvard, where he's been since 2004. Before that, he was at MIT. In a profession that has become increasingly specialized, Sendhil has chosen to tackle a wide variety of problems across numerous fields. If he specializes in anything, it's in bringing his keen insight and creativity to understanding the most important issues. He did some early work on corporate finance and governance as a grad student at Harvard when I first met him, but has since moved on to work on other problems. He has important work on discrimination, theoretical work on behavioral economics, econometric methods. He has applied behavioral economics to public policy and to issues around poverty, health, the media, and energy, to name a few. He's working on some medical issues he was just telling me about just a couple of moments ago. A few years ago, Sendhil collaborated with cognitive psychologist Eldar Shafir on scarcity, why having too little means so much. I love this book, but I will confess its opening paragraphs gave me pause before asking Sendhil to give this year's AFA lecture. The book begins with a description of one form of scarcity, time. And the example is Sendhil himself, who is overcommitted, chronically late, and non-responsive to emails. What if I send him an email and he doesn't respond? I thought. I needed an answer soon, in part because I'm also chronically late, overcommitted, and non-responsive to emails. And I was on a tight schedule. But knowing that Sendhil would do a great job, I launched the email anyway. The positive response was immediate. I was relieved, but with greater insight into why it is that Sendhil is so chronically overcommitted. He basically says yes to everything, and he says it quickly. Today, Sendhil is going to talk to us about a new line of work he has been exploring over the past couple of years. Another example of Sendhil's breadth, his creativity with which he approaches problems. This work explores the connection between machine learning, all the rage in the tech world, and econometrics, our bread and butter. In fact, he's working on a book making that connection, and today he's going to share his perspectives on how we can use machine learning in finance. Sendhil?
Thanks, David. I have to say it's an incredible treat to be here to give this lecture, given all the people who have given it before. It's also a particular treat for me because my job market was actually in Chicago, and that was God knows how many years, let's not count. I still, for the longest time, had painful memories every time you got near the AEAs. I think that never disappears, but there's some nostalgic value to being here, and I have a few David stories to tell. But let's start with machine learning. This is based on 4 papers, of which I'm going to focus on the first, which is with a grad student, Jan Spies. This is a JEP paper that'll be coming out soon. And what I really want to do is I want to start with a very simple kind of experience that you've all had. This is a photo of David. Now, most of you looking at this photo might be looking at this part of the photo and wondering, what was David arrested for? What is this a mugshot of? Which I have questions about myself, David. You might also be wondering, does HBS not pay enough to afford a tie? Which, you've got one now, so I don't know what was wrong there. But perhaps what's most interesting to me is when you actually take a photo like this with your phone, the one you have in your pocket, this shows up. You guys have all seen this. There's a red square that says that's where the face is. It's so automatic you don't even think about it. But isn't that weird? That your phone knows where in the photo the face is? Not just where the face is. You can go onto Facebook and they'll recommend that, oh, this face in your photo is probably this person. Who the face is. You can open up your phone and you can say to Siri, weather. Siri will understand those phonemes to mean the word W-E-A-T-H-E-R, not the word W-H-E-T-H-E-R. We'll take that, and then we'll be able to say to you, oh, what you probably mean by W-E-A-T-H-E-R is you want the weather in the place you're at. Let me go and get that on the web and give it back to you. That's unbelievable. Yet most people are like, oh, Siri's not very good. I don't know what you wanted from this magic trick, but maybe the rabbit will be a little cuter next time. So to me, at least, it's hard not to be wowed. And it has a little bit of feeling, if you really think about it, of being magical in this way of, how is this even happening? It's not like you can really figure this out. So it's kind of like, that's the question that I think 4 or 5 years ago sort of started with. And probably that question transformed into, well, could that magic, how it works, be used elsewhere? And of course, as is the governing principle of economics and finance, could I use that elsewhere? Self-interest. Let's start by looking, so that's what I'm going to do at the beginning of this talk, fairly briefly, to just walk through a very crude way and an easy way of trying to understand what's happening when machine learning does these tasks. I'm going to start with something simpler than vision, something more relatable, I think, is the better way of saying it. This isn't simpler. Actually, we've made less progress on this problem than we have on vision. Vision is the place we've made the most progress, but at least this is a place where I think we can all relate to it. And then I'm going to try and use that to illustrate how these work, and then we'll come back to how we might be able to use it. So let me start with a simpler problem, language. And in particular, I'm interested in a particular problem in language, an old problem called sentiment analysis. A sentiment here is not the way the asset pricing people in the room here are imagining sentiment. This is just, there's a piece of text. Is it positive or negative? For example, this is a product on Amazon. You've all been to Amazon. This is the Hutzler 571 banana slicer. I don't know what the 571 stands for. If, like with this product, as with many other products, you could go and look at reviews for this product. So for example, here's a review. I can read it for you, for those of you who can't read over there. I bought this in order to speed up cutting up a banana for my cereal. Any time I saved in that endeavor was spent cleaning this implement. It is not easy to clean. You have to scrub between every rung to thoroughly clean it. So that's the text. How many people here think that's a positive review? You can raise your hand. How many think it's a negative review? You can raise your hand. That's correct. You just did an active sentiment analysis, and you got it right. That was a 2-star review. Let's do a few more, just because really, besides these, I don't have anything else in my talk, so I got to make this last. So the next review is, once I figured out I had to peel the banana before using it, it works much better. How many people think this is a positive review? Raise your hand. How many people think this is a negative review? Oh, come on, this is an easy one. The guy loved it. Uncle Pookie says, great gift. All right, well, let's just, I was going to say sentiment analysis is an easy problem, but apparently not as easy for economists. And okay, let's keep going. So here's another review. Confusing. There's no way to tell if this is a standard or metric banana slicer. How many people think this is a negative review? Yes, this is a negative review. Correct. One more, I will stop. I will promise you this talk, unfortunately, peaks very early. The last one. I think I put this one in because this is my favorite one. I tried the banana slicer and found it unacceptable. As shown in the picture, the slices are curved from left to right. All of my bananas are bent the other way. How many people think this is I won't even ask you. This is obviously a negative review. I've also decided this will be the title of my autobiography. Let's move on. So how would we take a problem like this? The essence of how artificial intelligence worked starting in the late 60s was the recognition that this can't be hard. Why can't this be hard? Because we all do it so well. Like sentiment, you just show a bunch of people they're doing it. So it might be hard to build a 100-story skyscraper because that doesn't exist. But doing something that billions of people do should be pretty straightforward. And this is true of a lot of things. For example, Marvin Minsky, the famous artificial intelligence researcher, once assigned the problem of computer vision as a summer project. So here's what they thought they would do. They'd introspect. Well, we do it. How do we do it? Great. Let's program that up. So for example, with sentiment analysis, well, when we look at a review, what are the things we use to determine a positive or negative review? Let's make a list of those words. Let's turn each review into a vector of words, and then let's use a very complex algorithm known as counting. So let's try that. This is from a paper that did this with movie reviews, half positive, half negative. And so all they did was they got people to make up positive reviews. So for example, positive words. So dazzling, brilliant, cool, gripping, moving. These are all positive words that might happen in a movie review. Then they said, what are some negative words? Suck, cliched, off, slow, awful, bad. And then they said, let's apply this complex counting algorithm. Remember, half were positive, half were negative. What they found that by using this, you get to a 60% accuracy rate. That's not very good. You can get to 50-50 by flipping a coin. Worse than the 60% accuracy rate is the fact that in around 82% of the reviews, the algorithm said, I don't know, because none of these words appeared. And you might say, what a fool you are. Obviously, the problem is you need more words. And if I were to summarize artificial intelligence research from this period in the 1960s all the way up to sort of the early 90s, I would summarize it by more words. We're on the right track. We just need more words, more combinations of words. Let's just keep going. This was slow going, but we were sort of feeling that, well, sure, we do it perfectly, so our knowledge of how we do it must translate, but it just was not translating. If you went to 1988, when I was an undergraduate, I was in computer science, I would say that it felt like, actually, I'll tell you my own story. I like this story. When I was a grad student at Harvard, I had a friend, and he decided, I'm not doing economics anymore. He was doing a PhD. And he said, I'm going to do applied math. So then I started doing applied math. And one day I said, Daniel, what are you working on? He said, oh, I'm working on face recognition. I was like, face recognition? He said, oh, well, no. It's actually nose recognition. We look for noses and faces. And I was like, oh, really? He said, well, I don't want to, it's not just me working on it. Our entire lab works on nose recognition. It's a field. That was like the early 90s. It was a hard field. And here was the feeling that most people had. There was going to be some massive breakthrough, some deep insight that's going to unlock this problem. And then I didn't pay much attention to it. And then one day I was looking at Siri. I'm like, well, obviously we've gone well past nose recognition. Something has happened. So what's the magic trick? What was the breakthrough? So the breakthrough was very basic. It was, let's stop trying to reason this out. Let's just make this a purely empirical exercise. Let's get the data, whether it's movie reviews or photos or whatever, and let's just let the data speak. Let's just ask, not what do I think appears in a good review, but what actually appears in positive reviews. This may be a bit deflating because you're like, that's kind of obvious. Well, that obvious thing turned out to work amazingly well. It was learning, not programming. So for example, let's go back to that 2,000 data points. What are the most diagnostic words? Well, it turns out love, superb, great are some of the most diagnostic words. That is, they appear in positive reviews. The likelihood ratio is very high. Most likely to appear in a positive review relative to a negative review. What are the most diagnostic negative review words? Bad, stupid, worst. You'd be like, it's kind of obvious. But there are surprises. For example, one of the most diagnostic words is the word still. I don't think anybody in this room would have said, that makes my top 10 list. But it does make the top 5 list. For example, the acting was shitty, still I found myself enjoying it. It turns out still is very diagnostic. There are 2 other things that to me at least were very surprising. I never put it in there. One of them was a piece of punctuation. So I want you guys to guess what it is. This one was so surprising to me, it wasn't obvious even what the sign went, even though it was clearly diagnostic in one direction. Question mark. How many people think here question mark is diagnostic of a positive review? Raise your hand. How many think question mark is diagnostic of a negative review? Ah, that's pretty good. That's correct. As in, who would like this piece of shit? There was another one which was a big surprise. The big surprise was exclamation mark. How many people here think that exclamation mark is diagnostic of a negative review? Some. How many think exclamation mark is diagnostic of a positive review? A, I love your optimism and enthusiasm. B, you might want to get out on the internet a little bit more. Because if the internet teaches us anything, it's that people get really, really excited when they hate something. And it turns out exclamation mark is a very so all those exclamation marks in those teaching reviews, just think about it for a minute. With this type of approach, we've now gotten up to about 95% sentiment analyzers, which is kind of shocking. It's shocking because now it's so common, you can download R packages, which are sentiment analyzing packages that just off the box, we kind of know what makes good. So let me summarize what I think is a good way to think about machine learning and what gives it an interface with what we do, which is it's basically turning intelligence in an empirical task. Specify what is to be predicted. Presence of face, not good review, bad review. Just a binary variable in these cases. Specify what you're going to use to predict it. Vector of words, vector of combinations of words. Even face recognition is just this. So for example, a very common face recognition task can be just written as something you're very familiar with. Y is 0, 1, presence of face. X is 0, 1 to J, G, the grayscale in that pixel. So an image is a 24 by 24 pixelated square. So there you go. It's just 0, 1 to G to 24 by 24. That's all it is. That's just the X vectors. And then what are you looking for? You're looking for an F hat. What is an F hat? It says, if I classify an f of x as having a 1 or a 0, and the true y is a 1 or 0, I have a loss function. I'm looking for a f hat that minimizes expected loss. That's machine learning. That's it. In fact, it's underneath most machine intelligence that you see. There's a few exceptions, but really everything else. And this is interesting because it might help you understand why machine learning rose now when it did. It's not a coincidence that the two big bubbles of our time are big data and machine learning. Machine learning very much relies in a fundamental way on having data points. A sentiment analyzer, as I'll show you in a little bit, that uses 1,000 data points is not going to be as good as one that uses 10,000 or 100,000 or 500,000. So you might say, this is great. In fact, it's good for these engineers that they've discovered the field of statistics. I'm glad. We've known about that for a long time, and there's not much for me to learn here. And I think it's partly true. So for example, some of the most interesting developments in face recognition were really nothing more than applying PCA, which we all know, to face recognition. And for me, it's one of the reasons that it's hard to penetrate this literature, because in a machine learning paper or in a machine learning book, you'll see them talking about logit regressions with the same breadth that they talk about something you haven't heard of, like random forests. And you're like, I know what a logit is, so what's new here? But I don't think that that is the full story. And I think that to understand what machine learning can offer us, it's important to understand one feature of it that is essential. And to do that, let's go back to the sentiment analyzing context. And let's look at a table from that paper that might be useful. So each row here in this table is about 3 algorithms that they ran. We'll ignore the 3 algorithms, what they are. I'll just tell you what the rows are. The rows for them were the kind of x variables that were given to the algorithm. The y variable is positive, negative sentiment. So the first row says, oh, am I going to put unigrams? By unigrams, we just mean presence of a word, or in this case, frequency, number, percentage, or how often does this word appear for all possible words in the lexicon. So here's another one, unigrams plus bigrams. And this is all fine and well, and you can see they have their performance here. I think the noteworthy thing about this table is this column. This is the number of variables on the right-hand side, effectively. About 16,000 for unigrams, about 32,000 for, that's fine. That's the number of variables on the right-hand side. Except you'll remember I told you they have 2,000 sample points. Now, you might remember this basic fact from statistics that you probably shouldn't be running. I mean, you can run regressions with more data on the right than you have data points, more variables on the right than you have data points, and it might even be a very good way to get tenure. But as long as you clean up stuff afterwards. So really, how are they even doing this? And if you think about it, this is the heart of what machine learning has to offer us. There's a lot of machine learning that will look like the type of things you already know, but there's a part of it that is really novel for what most people here and me kind of know. It's a high-dimensional statistical procedure, by which I mean the full rank condition is violated. Yet somehow, despite this, now if you remember when the full rank condition is violated, the problem is not that you can't find an F hat that works. The problem is lots and lots of F hats work in the data you have. That's useless. What you want is something that does well on a new data point. So machine learning somehow manages to fit, despite this high dimensionality, and do well on a new data point. So the question is, how? And that's what I want to sort of talk through a little bit of how it's doing it. And to do that, I'm going to try and work through an example that Jan and I have been working with, just as an illustrative example. So this is the American Housing Survey. So in the American Housing Survey, which many of you are familiar with, we've got characteristics of houses, and you've got house prices, or at least the person's stated subjective value of the house, which I'm going to call house price for purposes of today. And you might say, I'm interested in predicting house price. You might care about this for a wide variety of reasons, that you want to get a Y variable, value of the house, given the characteristics of the house and the things you know about it. Here's what OLS does. Its out-of-sample performance is about 42% 42% R-squared. Now, what's interesting about this is in this example, already one of the tensions shows up in using machine learning in our work. It almost feels like there's nothing high dimensional here. What do I mean by that? It's easy to think about high dimensionality in the language examples, just because when you just start counting words, you're already at 20,000. Here, the American Housing Survey blesses us with 142 variables. But we've got thousands and tens of thousands of data points. So what's high dimensional here? And that's important because I think if I were to just poll people and ask them about, oh, what do you know about machine learning, I think a lot of social scientists would know probably the first thing they would say is lasso. Is probably the most likely answer. And with lasso, you'd be like, what am I going to lasso here? It's 142 variables. But is that really true? What is a variable? We're so used to running regressions, we say, oh, we have 142 variables, but that's not really right. I mean, there could be interactions of variables. There could be triple interactions. 142 to the k power can get very big, very fast. So really, this is one of the kind of mind-opening things that help me understand things. The default that we turn to, let me run a linear regression, I have 142 variables, interactions are this exotic thing that I might add, is a way we have of approaching the problem that's our default way of approaching the problem, but there's nothing odd, there's nothing special about linear regressions, and I'll come back to that later. So more generally, when you think about high dimensional, you shouldn't be thinking about number of variables. It's not a counting exercise on the right. It's all the ways in which we're allowed to combine the variables. So it's no longer about k greater than n, where k is counting number of variables. It's the dimensionality of the function class that you're choosing to use. Linear functions have the simple property that you can just count on the number, and that gives you the dimensionality. But for many function classes, the dimensionality of the function class is usually parameterized in other ways. So let's make that concrete. Let's talk about a very, very simple function class that we can all understand, decision trees. So here's a function that I could define. Pick a variable, any variable you want. So that's the first thing. Split on that variable. For example, do you have less than 7 rooms in this house, 6.5 rooms in this house? So this is a depth 1 decision tree. You can count how many depth 1 decision trees we can form. It's the number of variables we have available to us times the number of values they take. Those are the splits. That would be the dimensionality of depth 1 dimension trees. Does that make sense to everybody? Pretty straightforward. Of course, this is not a very interesting function class. There are only a few things we can do with this. So let's go to depth 2. If there are less than 7 rooms, in this, go to the right, and then you decide, are you in region 2, 3, then stop. If there are more than 7 rooms, ask if there's this much square footage, and then stop. Of course, no reason to go there. You can keep going. Decision trees are explosive. Even down to level 7, you now have 2 to the 7 at the bottom. So there's quite a lot of combinations that you can get, even with fairly shallow decision trees. This is just another function class. It's just like a linear model. Is it more right, less right? Who knows? It's just a function class. Even with the housing survey, with 142 variables, I can build arbitrarily complex decision trees. Just so you get an intuition for how these function classes operate, here's one thing I found helpful. Here's, with just 2 variables, here's what OLS might look like, okay? It's some gradient in this space. I've colored this as a function of the y hat value. So if I had a particular regression, I might have sort of, as I move in this direction, it goes lower, it goes higher in this direction. This is sort of an isoquant line, so you can kind of see what OLS looks like. What does a decision tree look like? Well, a decision tree with just two variables, even without much depth, kind of looks like this. The first split is less than or bigger than, I think I have a number of something on the bottom. It's fine, less than or bigger than the x1 variable. The second split is less than or bigger than the x1 variable at a different value, because now I'm pinning off that stripe. The next split is up here, and the next split is over here, and now I have a grid. And then I give a value to everybody in that cell. A decision tree is a little bit like a local estimator. It's a nearest neighbor. But what's beautiful about a decision tree is that the neighbor is being decided upon by the algorithm. It's not a God-given neighbor. For example, everybody in this cell has a huge set of neighbors, whereas everybody in this cell has just these neighbors. Everybody here has their neighbors defined by this stripe. So decision tree is sort of an endogenous allocation of who goes with what. Okay, so that's a function class. So once you realize that, you realize, well, in the American Housing Survey, we could just fit a decision tree. But it raises a question, a decision tree of what depth? Now, the good news is, the deeper we make our tree, the better the fit, because we can better approximate the data. Does that make sense to everybody? The grids are just getting smaller and smaller. Of course, you might know what the bad news is. The bad news is, the deeper the tree, the more we overfit. In fact, make a deep enough tree, and unless points are laying on top of each other, every point can have its own cell. You can repeat each cell's own value. You've really just repeated the data. It's very quickly you can violate the full rank condition with the decision tree. Just a way of saying that data has signal and noise. Overfitting happens when we fit the noise more than we're fitting the signal. Deeper trees pick up more signal, but they also pick up more noise. So what do we do about this? I think if you can understand how machine learning solves this problem of choosing decision trees of different depth, then I think you'll see where the sort of magic is, in the sense that how is it able to do high dimensional statistics? And I think it's right here at this point. And I think that if I were to think about what we do a lot in non-parametric statistics before, 95% of it would have tried to put some bounds and say, well, let's let the depth of the tree grow with sample size, do this, do that. I'm going to show you a different procedure, which most algorithms tend to use, and I think it's that procedure that really unlocked something for us. So let's start. This is called regularization. The procedure is very simple. It says, let's just define for the trees a natural variable that defines how complex they are. In this case, let's call it the depth of the tree. Okay, how far down am I going? And let's fix that. So let me say that I'm going to find the tree of that depth, the best tree. So this solves overfitting, because now I fixed the depth, but only partly because I'm left with the problem I just told you, what depth to choose. So let's dig deep on that. Now I've fixed the depth. What depth do I pick? Let's understand what we want. We have a sample. We can measure how well any f hat does in loss terms, in predictive quality in that sample. That's the empirical average in that sample of the loss of any f hat. That we can measure. What we want is the expected loss in a new piece of data. But of course, we only have this. So we want out-of-sample performance. We only have in-sample performance. And this is another way to understand our problem. In sample, we know the tree that's going to fit best, the deepest tree. Okay. Just so you get a sense, this is not a new problem. This is an old problem. Traditional model selection involves putting structural assumptions on the data generating process to approximate what the performance of the empirical fit will be relative to this. You've all seen this. Maybe you don't realize you've seen this. How many people in this room have looked at an adjusted R squared? You've all looked at an adjusted R squared. Do you know what the adjustment is? This is the adjustment. OLS overfits. Every estimator overfits. That's the overfit assumption. How can we make it? We make it by putting structural assumptions. A true data process is a linear process. I can adjust for it. So when we know the data generating process, that's what we're doing. We're saying, I see the in-sample fit, my R squared. I would never report the R squared. I'm going to report the adjusted R squared. So there you are. This is great. So one way to do model selection is to say, I've got my in sample converted to what my guess is of the. Of course, you see the problem here. If I knew the data generating process, why am I doing this activity? That's the machine learning conundrum. I mean, if I knew how faces turned into, that's not, I don't even know what you're telling me if you knew the data generating process. So they kind of needed a different approach. And the different approach is shockingly simple. It says, don't use all your data. Take this data, train on this small subset, or big subset, whatever. Train on this subset. Hold this part out. Let's call this the train set, this the tune set. Now, I'm not talking about hold out to evaluate performance. I'm just saying there's a different use of holdouts. Don't confuse that. This is really the magical part of this. It's the use of another piece of data, one that this algorithm hasn't seen, to then say, I can measure my performance on the training data set, but I can also measure the performance of an algorithm trained here on this training data, on this tuning data set. Why is that useful? It's useful because what I can now do is remember, I had reduced the problem of choosing the best decision tree down to one parameter, the problem of choosing depth. So now I can fit trees of every depth on the x-axis and see what performance looks like on this other tuning data set. It's kind of magical if you think about it. The data is telling me, so here's the in-sample performance. As the trees get more complex, in-sample fit gets better and better and better, of course. But, and that's true for quite a period, but at some point, out-of-sample performance starts to get worse. So you would pick this level of complexity. That's the level of complexity at which the overfitting is now dominating the problem. We're picking up noise more than we're picking up signal. Think of how amazing this is. This is giving us a way to actually see the overfit empirically and let the data tune for us how complex a model we can fit. And this is amazing in part because to me, it tells us, like if I had gone in and I had a data set, I'd say, let me try this and let me try some interactions maybe. Here, the algorithm is trying and figuring out what complexity the data can hold. The difference between me mucking around with it and the algorithm mucking around with it is that we can't reproduce what I did at every level of complexity and know that I'm not polluted by what I saw. The algorithm brilliantly can just reset and say, well, I tried depth 24, and now I'm going to try depth 25. There's no knowledge transferring from depth level to depth level. It's just what happens at each level. I want to take a moment at this because I think this is such a profound insight. A bunch of things that my intuitions had built around in the way I normally deal with econometrics no longer hold when we're doing this. So here's an intuition I tend to have. Sample size. Sample size is like 1 over square root of n, tweak standard errors down. People even say this. You write a paper and they're like, why did you need 500,000 data points to show this? It must not be a very big effect. And that's the intuition they have. It's marginal, it's small, 1 over square root of n. And for hypothesis testing, that is how standard errors largely go. They go 1 over square root of n, and we kind of have that intuition. You'll all notice that here, sample size does something else in addition to your usual intuitions. If I have more sample, you can see how the complexity that the data can hold moves to the right, because I need an even deeper decision tree before I start overfitting. Which means, with better samples, I'm not just getting tighter error bars around a fixed prediction. I'm predicting better and better and better. One of the most famous papers on this, which led to an intuition on this, was by Benko and Brill, which I really like. It's from natural language processing. It's actually on a task. It's a task I alluded to when I talked about Siri. When you hear the word weather in a sentence, how do you know whether I'm talking about the word, like I just said, weather, W-A-T-H-E-R, or whether I'm talking about the word W-H-E-T-H-E-R, or the word W-E-A-T-H-E-R, just disambiguation. That's what they do here. They basically say we're going to produce these learning curves for confusion set disambiguation. Here's a point Benko and Brill make. Each of these points is a different algorithm. What they used to call perceptrons, now people call neural networks, naive Bayes, all these things. But that wasn't Benko and Brill's point. Benko and Brill's point was we trained these algorithms using 100,000 words, and we got to performance of about 75% in the worst case, 82% in the best case. Then we gave it 1 million, performance still goes up. 10 million, performance is still going up. 100 million, performance is still going up. Billion, performance is still going up. It's kind of an interesting thing. This is why these algorithms are so data hungry. Performance keeps going up because they're able to hold more and more structure of the problem without overfitting. Another thing to notice in this thing, notice the dominant force here is sample size. The difference between algorithms is a lot less important than just having more raw data, which is kind of another useful intuition. So let's go to the AHS data. Let's have a look what happened there. So that was OLS. The tree does a little better, 44.8. But of course, that's not the only model available to us. I won't go into what these are. You can read about what they are. You can do a forest. That gets us to 52.6%. You can mix forests and trees, and you get about 53.1%. And this is just us very crudely off the shelf, sort of whatever. So if you expected 42% to become 90%, that's not going to happen. This is social science. If you thought, oh, I was throwing away 20 to 25% of the predictable variation in this data, that is right, by just using the linear regression. And that, in general, is, I think, a good way to understand what these algorithms can do. In some data sets, they can find a lot more structure than we imagined that are there. And the AHS is something I think many people in this room have used, and it's not that odd of a data set, and you can just do noticeably better. So one way to, let me summarize this discussion. Algorithms really are just you might read about them, neural net, this, that. What they really are is a statement about functional forms, which you're all familiar with. The F is drawn from some class of functions, okay? With a regularizer. The regularizer is a thing that determines what is the complexity. When I decide to have a simple function, like low depth tree, how do I adjust the complexity of the function? It's a measure of what is more or less complex. An example, going back to something you're all familiar with, in Lasso, you might say, the regularizer is the L1 norm. With Ridge, which some of you might be familiar with, it's the L2 norm, but the function class in both cases is a linear function. So this is an easy way to parse pretty much every supervised machine learning algorithm you'll ever see. It's an easy question you can ask. And in some problems, you can get pretty sizable improvements over what you would just do if you just picked out a thing and ran a lasso. So I started by saying these guys are doing stuff that we already know. But now I seem to be saying what I've done in the past is fit Y with X. This fits Y with X and does well out of sample. That's a nice bonus. What I used to do was low dimensional. What I do is high dimensional. What this does is high dimensional. So now from saying, is this have any value to me, you kind of almost have to ask, is this just better? Like, why am I doing any of the stuff that I ever did? It's just a better tool. And it is absolutely not better. There is, in my view, one very important distinction. And if you don't understand this distinction, in my view, it's very easy to get machine learning algorithms deeply wrong. And you can already see it in the nature of how they're built and what I built up to. And once you understand that, I will say that I think they're different tools. They serve different purposes. So let's dive in. Let's just remind ourselves what the goal of prediction was. The goal of prediction was loss minimization. It's kind of like pick the F hat that does well on a new data point out of sample. Okay, I know loss minimization. Yeah, I know what that is. That's fine. But that wasn't the goal of estimators. The goal of estimators was unbiasedness. The goal of estimators was to say that I'm getting an F hat that in some space is in expectation the right thing. This is important. For example, you all remember that OLS is blue. I don't know if you guys remember this. It's the best linear unbiased estimator. You know that OLS is not the best linear predictor? Which is weird. How could the best linear unbiased estimator not be the best predictor? Because the best predictor has bias coefficients. That's very basic, and that issue shows up a lot in high-dimensional estimation. And to really see why that issue is so fundamental in high-dimensional estimation, let me give you some examples from the low-dimensional case just to remind you of stuff. So let's suppose I run a linear regression, and V and W are both correlated with each other, okay? And correlated with Y. What happens to the standard errors in your linear regression? Individual standard errors on V and W now blow up. Why do they blow up? Because you don't know, you know that V plus W is correlated with Y, but you don't know which one's doing the work. As a result, the individual standard errors now get very big. That's because OLS is trying to tell you about making inference on specific coefficients. What happens in a prediction model? If V and W start being correlated, it doesn't matter which one you pick. In fact, take V and W towards each other towards perfect correlation. The algorithm's like, great, now it really doesn't matter which one I pick. Because for prediction purposes, the correlation is your friend. You don't need to adjudicate. Prediction does not adjudicate between variables that serve similar purposes. Here's another example. Suppose that you ran a linear regression and somebody said, hey, you've omitted this important Z variable. In an estimation world, you'd be like, oh yes, this is what a seminar feels like. What would happen in a prediction world? You'd say, great, because it means the variable that I measured are also picking up on things I didn't measure? Even better. Because again, in terms of predicting Y hat, it doesn't matter for that purpose. You could say, maybe if I got that variable, it would help me too, but it's a different kind of comment. It's not a your coefficients are biased. This is all really magnifies in a high-dimensional space. Let's go back to the full rank condition. The full rank condition is so problematic. When it's violated, it's so problematic because so many different variables can be diced back together to make the data. For prediction, I don't care if you recombine a bunch of variables together to make the same data, as long as it's doing pretty well out of sample. I don't need to attribute the coefficients correctly to the right place. In other words, if two functions are similar in output space, however different they are in coefficient space, that's good for prediction. But it's very bad for estimation. And this problem becomes very severe, and there's one branch of the literature that makes very specific assumptions about the data generating process, assumptions you might believe in some examples, and says, yes, but if you believe the world works like this, I can do high-dimensional estimation and get coefficients. But out of the box, without making a lot of strong assumptions, one way to understand is once you see the goals of prediction and estimation are different, you can go back and say, oh, I see. The loss function is the primitive. That's the only thing prediction is doing. When I do estimation and OLS minimizes quadratic loss, that's not the primitive. It's not minimizing quadratic loss and telling me I've minimized it. It's saying, I've used that, don't worry about that, but I'm guaranteeing you unbiased coefficients. Does that make sense to everybody? So I've almost kind of want to illustrate to you how much this matters in the AHS survey, so let me show that. So we went and in the things I just showed you, same housing prices, because lasso is very easy to understand. We just ran a lasso regression using, I think, around 300 and something variables. We did a bunch of pairwise interactions, and we just put them in on the right-hand side. And what I'm now going to show you is, I want to show you how beta hats look. So I'm going to take my data, I'm going to slice it up. And in each slice, I'm going to estimate lasso. And I'm going to show you in that slice which variables were picked by lasso. Does that make sense to everybody? So let's just look. And what you find is the slices are on this axis. The variables are on the y-axis. Of course, some variables are picked pretty consistently across all the slices. But you'll notice the noteworthy thing here is between slices, very different picks. That's not just because the algorithm's volatile. Here's performance of lasso. It's very constant across the slices in predictive performance. This is the essential nature of instability in prediction. There are many different ways to recombine things in high-dimensional spaces to get this similar enough y-hats that I can be very similar in y-hats, but be very, very different in coefficient space. Does that make sense to everybody? Okay. So as a result, what I would sort of say is estimation versus prediction. One backs out parameters, the other backs out predictions. To get parameters, we make the low-dimensional assumption. To get prediction, we choose to make a high-dimensional assumption, and we don't adjudicate between observably similar functions. If you want a cartoon version of my thinking, which probably is actually my version of thinking, so is that estimation is perfect for beta hat problems. Prediction is perfect for y-hat problems. And you can see why face detection is a y-hat problem. We're not looking to the algorithm to tell me the deep geometry that makes faces. We're looking for it to find the face. At this point, you might say, great for engineers, but I'm interested in coefficients. In fact, I don't know if you've been to a seminar recently. People in this field don't just care about coefficients. They go past that and say, but the coefficients aren't causal. So you're not even telling me this isn't causal inference. You're telling me you don't even get meaningful coefficients. You're not even getting unbiasedness in this most trivial sense. What use is a procedure where even the coefficients aren't meaningful? There isn't one, and it's 40 minutes, so I'm done. This is it. No, that'd be a good way to end this talk, wouldn't it? I do have some uses. So I'm going to talk about applying prediction, and I'm going to talk about 3 applications, but let me do 2 at first, and we'll see if we make it through those. I might skip the third. The first application is actually prediction unlocks for us new kinds of data. So you can continue doing estimation as much as you want, but using the prediction component to unlock data that you normally don't think of as data. This is the easiest glide path into this field because you just do what you always did, except there's a little black box that produces data for you. That black box is not called the grad student. That's actually the algorithm. The second way is I'm going to say that there are problems where we may want new ways of analyzing data we already have for old problems, like the AHS. So let's break these up. Let me start with the new kinds of data, and then I'll move to the new ways to analyze. When I was a grad student, I still remember, I think I'm going to get the dates wrong, and someone will call me out on it, but I think it was like sometime in like 1990 when like TAC became really big. Is that right? Sometime in that period? Because I remember people being super excited, like, oh, now we can get transaction level data, like actually, each trade. And I remember people being like, what would store all of this? This is like 25 million rows per day, 1 gigabyte per day of data. And like, how would we manage it? How would we work it? Of course, the world's changed since then. For example, we have, I've blurred out who this tweet is, but we have tweets now. I didn't want to embarrass anybody, but it's a tweet by a famous person. We have tweets, and tweets have 500 million tweets per day and about 2 terabytes or 2,000 gigabytes per day. If you want to think about a huge amount of data that's come into the system, that's a lot more data that's coming into the system. We have Google searches. We have message boards. We just have this insane amount of data that is now potentially on the right-hand side or on the left-hand side of our variables. This data, I think, is very informative. I have to tell you my favorite one of these, because it's fun, is a grad student of mine walked in and she showed me Laura Trucco, who's on the market this year. She's terrific. She showed me this graph. This is Google Trends. This is just search data. So this is people searching for the phrase iPhone slow. Okay? Those are some very interesting spikes in the data. This is over a 7-year period. Any guesses what those spikes are? That's correct. All of you have. These are the releases of new iPhones. So I have a tin hat, but I can lend it to you if you'd like, if this is a... So, of course, it's not just Laura's insight. Hal Varian and Choi have some very interesting work, and it's led to this where they use Google searches to show things like, if you want to predict Chevrolet sales, it turns out that Google searches predict it extremely well. So if you want early indicators, well before Chevrolet ever announces the number of cars sold, well, you kind of have to, a lot of people search for going to find a dealership, for going to go find things. This is just car dealers. In their paper, they have a huge number of fundamental economic indicators that are revealed by Google Trends, or the Google search terms. Unemployment, industrial production, various things. This is not just language data. I'll go through a few examples. This is another one of my favorite pictures. This was put out by NASA. This is a picture in Asia of an Asian country, which is an island separated from mainland China. Anybody know what the country is? This is a nighttime satellite photo of North Korea, which is the Korea that's right here. Why is this interesting? Because a whole branch of work has realized, wow, we can use nighttime satellite photos to estimate GDP. Because while North Korea says our GDP is terrific and we're really grown like 500% in the last 15 years, all this growth is apparently happening during the day. That has led to a whole industry that is very specific. Here's a more nuanced one. These are daytime satellite photos of crops. And you can see where we're going with this. You can actually use this. NOAA's done work on this. Quite a few people are doing this to actually measure crop yield down to much smaller than square kilometer levels at this point. Here's another one that's quite nice. These are all photos of, what are they called? The things that hold oil and gas? Yeah, there's a name for it. Sorry, I should have. So you know what these are useful for? You can see how much oil is in each of these. And as a result, you can actually get pretty good oil estimation of stocks currently, which people are now doing using satellite photos. Satellite photos are now super cheap, remarkably, and you can get real-time measures. Here's the last one I'll do on photos because I really like. This is, I think, factories in China. You can see what we're about to estimate with this. Industrial production, because you can literally see the rate of production. Of course, you could say, this is all great. What does this have to do with machine learning? What this has to do with machine learning is because before you can even get to things like production, GDP, you have a face recognition-like problem. I have images, except in this case, I'm not asking you to predict presence of face. I'm asking you to predict GDP. I'm giving you a bunch of satellite photos. I'm asking you to predict agricultural yield. So typically, the way these things work is that I get some rich data, language, image of tweets, where the input is merely pixels or words. You need some processing to make this into meaningful data, so you have a way of merging this data to something else. Like in that photo, this was my known yield. This was the amount of oil. And then I run it through machine learning, and that gives me a simpler data set, which is of the type, yeah, don't worry about the photo. Here is the estimated yield for this region. This processing step can actually, in and of itself, produce some pretty amazing insights. So let me give you an example of this, which I really like. This is there's a few papers on this. I chose the later one on PNAS. The earlier one was from Science, but this is a very nice paper from PNAS. Here's an abstract in PNAS, Proceedings of the National Academy of Sciences. These scholars simply took all of these abstracts, and they simply categorized them by the kind of words that are found, and had the algorithm sort these. This is called LDA. It's just a procedure. Sort these into categories, meaningful clusters of these words. Why did they do this? They did this because then they could recover from these abstracts what the algorithm thought were the categories. What's really quite fascinating about that is that they actually recover pretty well some of the most interesting categories. In fact, if I were just to line up what they recovered, so on the, on the x-axis, if I were to line up, these are the categories the algorithm found. On the y-axis was the categories that the editors put things in. The algorithm, without ever knowing these, simply, notice it just found a diagonal line. And in most cases, when it found some differences, it's because population biology had actually split into 3 or 4 new fields. This was so interesting, however, because you also see a little bit the downside of this. There was one category that it found, which is a fascinating one, category 109, which was defined by words, research, new, information, understanding, paper. I feel like I've written these papers. What's so nice about this is you can also see how, because you really have a corpus of data, you can get to evolution of topics over time. So theoretical physics is a fixed category, but the words that define it have changed dramatically in the 120 years of data that they have. It used to be force. Relativity had its moment. Laser really took off. You really see it in neuroscience. It's fascinating. Nerves, nobody studies anymore, but neurons, everybody studies. So this example I like because from it, I hope you guys can all really see where I'm leading you. There's a very obvious application of this. You guys see this? Well, this is like studying academic industries. Well, the same technique could study business industries. We're using abstracts, We could also use the product descriptions in 10Ks. We've had humans categorized by SCCs. So there's a very nice paper by Hoberg and Phillips in the JPE. It's not quite LDA, but it's very much in this direction where they sort of use text-based SIC classification. I think this is a very promising area because, I don't know if you remember, David, we did this long time ago, this input-output type table where we were trying to figure this out. And we all know the industry categorizations are not obviously correct. Firms fit in many categories. We know it's not quite right, but we're forced to sort of categorize. Here we have a chance to take all of the text and find something. They have some cool results in that paper. I think in the interest of time, I won't go to it. They basically show that relative to the SIC categories, their categorization produces a lot more spread between the industries, a lot more correlation within industries, more differences between them. And they also find very much similarly like to the LDA, the same firm can kind of migrate across categories, and categories can change dramatically over time. So there are other applications. I think if I were to put money on it, I think vision is going to be very helpful in certain asset pricing finance type things because we get so much visibility into the real economy. But language is going to have a huge amount of benefit because we already you don't have to go find somebody to sell you satellite photos. The 10K forms are already there. And in fact, more than 10K forms, companies talk a lot. They tell you a lot of things. And so here's data on 10K forms from a very nice paper by Kogan et al. I mean, just look at the sheer number of words that were produced in 1996. The sheer number of documents are 1,400. And do these words have any value? So this paper kind of shows, actually they do. If I were to simply predict volatility, I can predict volatility using, let's start with the first column. I can predict volatility pretty well using past volatility. But without knowing anything about past volatility, I can predict it very well just using the words in the 10K form. But even conditional on past volatility, the 10K form adds a lot of information. So this is just almost a proof of concept. If you cared about volatility, the data that's in that language is clearly telling you something. There's other ways you can look at this. People have started to look at sentiment, not just in the 10K forms, but in MD&A agreements, on message boards. There's just a ton of just exhaust, so to speak, as people in this literature pay attention to. So I guess I'd say that's the first form, is the new kinds of data. And what I kind of want to do is to move from that to talk about new ways to analyze data. So here, I want to just remind you that one reason that I think this stuff is an even better fit in finance than in economics is that at its core, asset pricing is predictive. And I think as a result, who cares about Y hat? Finance cares about Y hat. It is actually a meaningfully important outcome in finance. There's a very nice paper by Moritz and Zimmerman that tries to use this. It's sort of a nice starting point, which says, well, we have this whole literature in asset pricing that's like, you could almost call it a human data mining exercise. If I were to be, it's not uncharitable, I really mean that is what we're doing, which is we'd like to know return predictability. So I'm going to take a bunch of variables on the right, and I'm going to try to mine through it and say, I have found another factor, or I found another thing that predicts. That's exactly what this tool is. It's automated data mining. What's the difference? Here, because we know what the algorithm is doing, we can apply, for example, Moritz and Zimmerman apply a decision tree-like algorithm to say, oh, look, I'm going to predict returns, but now you should be less concerned that I just data mine to find this because it's all out of sample. And you know it's out of sample because the algorithm was doing it, not me who went and peeked at the thing I claimed was out of sample. This is a nice early paper on this. But I would say that while these examples are totally intuitive to you guys, and as a result, I'll spend less time on them because I'm imagining that they will be very, just top of mind for you. Let me talk about a few less obvious ones. They may move away from asset pricing. The first one I want to talk about is that I bet you everyone in this room has run a regression of the following type. I want to control for something, by which I mean I care about this thing, but I need to control for these things. You've all done this. And you make this identification assumption. You say the TI is orthogonal condition. There's no correlation. That's a typo. That should be TI, not DI. So you've done that. Now what I want to point out to you is in some very intuitive way, controlling is predicting. And let me give you why. You care about this tau hat. You care about this coefficient. you really don't care about these coefficients. This is like semi-parametrics. This really is, in some ways, predicting the residual is like a y-hat problem. For example, how many people here have reported the main coefficient? All of you. How many people here have just said fixed effects? Yes. So it's hard to say I really was fascinated by the fixed effect coefficients when it is summarized by 3 letters. And what this means, however, is you'll notice that what I really want from these controls is to soak up all of the residual variation. And when I'm trying to soak up all the residual variation, it's a little bit like I'm trying to predict that other part, which in turn means better prediction in these cases means better identification, because I've controlled as much as I can. It's not a bad intuition. And I think that this way of thinking is probably going to pull in, and there's a bunch of papers that are starting to move in this direction, as sort of a new era of applied semi-parametrics. Even when you care about unbiased or causal inference on a particular set of variables, there's no reason you should be controlling for the rest in such a parametric way. That doesn't make any sense. One version of this, which I will describe, I won't go through the example in the interest of time, is an intuitive way of thinking about this is if you're interested in, say, the impact of a particular variable x0, and you believe x0 should matter. Here's a fairly simple procedure that we've used in one finance example. Predict y using everything in your data set. Just a black box machine learning algorithm. Just predict it. The coefficients are meaningless, but so what? Then predict y using everything but the variables that you think matter. And then ask, am I actually predicting better? That starts to give you a hint of how you might do something a little different. There's some screws to tighten here, there's some issues to deal with, but that's a different approach. That's saying, I'm not going to put in the one variable I care about and then add a few controls. It's saying, can I beat, by using the variable I think is informative, can I beat all the other stuff that I think, whatever, it's something else, it's unrelated to what I do. We've done this, I think I'll skip this. We did this for the disposition effect, and I can come back to that. There's a whole set of things. Jan, my co-author on this, who is more of an econometrician than I am, he even knows how to spell OLS. He put this together as a few examples. For example, let me go to one that I think is very nice. Instrumental variables. Instrumental variables is a very good example of a prediction component in these problems, and you can see how that is. When you run y on, let's say, x, and you instrument x with w, well, you have 2 stages, w on x, and then you have the second stage. Well, what comes out of the first stage? It's a hat. And you'll notice this in most IV papers. There's a bit of fishing going on. Which functional form of W? Do I use the binary version? Even when you look at papers that do things like weather, weather isn't a given variable. Oh, above 75. Well, let's try temperature quadratically. Let's try. So there's many ways it could go in. That is a prediction problem. IV has a prediction component in it. And I think as you reflect, a lot of econometrics you do has a prediction problem. I did the controlling for identification. So there's a bunch of very interesting econometrics papers that are coming out that I think will start pushing us in that direction. So this is new ways to analyze data. Let me move to the last one because that's the one that I think is interesting. This moves us a bit out of finance, but I think that things that look like they were out of finance 10 years ago now look like they're solidly in finance. So let's talk a little bit about it. So what I want to talk about is new questions. This question I want to talk about is a problem that's pretty big in the US. There are about 12 million arrests in the United States. And one of the interesting things about when you're arrested is the first thing that happens to you, I mean, besides all the brutal stuff, is that you go before a judge, and that judge has to make a decision about what's going to happen to you. This has nothing to do with whether you're guilty of your crime. The decision is very straightforward. It's whether you'll spend the time between now and when your case is decided upon here in jail, or whether you'll spend it at home. In other words, will you be released while waiting for trial? Bail is involved in this, if you've ever heard of this. There are about 750,000 people at any point in jail in the United States. I didn't know this until I started this, but jail is almost exclusively, not exclusively, but primarily people who are simply waiting for trial. So that's 750,000 people who are not guilty of anything, or they may be, but they haven't been found guilty. They're just waiting. And it's not a short wait. The typical wait is about 2 to 3 months. In some jurisdictions, it's about up to 9 to 12 months. It's crazy. That's super consequential for these guys. Why am I raising this? Well, what is the judge doing when making this? Well, we know by law what the judge is doing. Depending on the state, the judge is asked to consider either only one thing or two things. In some states, it's will the person appear if we let them go? That is the sole thing they're asked to predict. In other cases, they're asked to predict will they appear, do they pose a flight risk, and a public safety risk, will they commit another crime? So, but you see what this is. This is just a why hat problem. Isn't it amazing that we have humans solving 12 million times a year a why hat problem? And unlike face detection, where we're pretty sure humans are near the boundary of what can be done on this problem, we don't really think we're going to have, really big breakthroughs in most naturally occurring face detection problems. So you can imagine in spy technology, et cetera, I couldn't tell who that was, but the algorithm can tell who that was. Here, there's no reason to know whether judges are doing a good job or a bad job. This is what I mean about a new problem. This is a why hat problem. Why don't I take all of this data, form my own predictor, and compare the judge to this predictor? Where do we go from that? Well, let's at least see what's happening. So this is our predicted risk on the x-axis. This is the release rate of the judges. We don't know the judges' predictions, but we know their implicit predictions that's embodied in their release rate. So looks like we agree over here. More risk, lower release. So let's call that the agreement region. Low risk, high release. But what's kind of funny is I would argue that we don't agree here. What do I mean by we don't agree? We don't know who's right, but what I would argue is we don't agree here is notice that the algorithm says, well, the judge is saying, well, half these people are not risky. The algorithm is saying these people have a 60% chance of committing a crime. That's a pretty big wide range. And in fact, let's figure out who's right. So on this sample, this narrow sample, you can look. You can say, let's look at all the people who are released in that cell. Let's see who goes on to commit a crime. And in fact, you find that this rightmost cell, the very high predicted risk, 60%, the algorithm doesn't quite get it right, but it gets to about 55% predicted risk. That means there's a identifiable group of people who have above coin flip chance of committing a crime, who the judges are releasing at about half, slightly above half rates. On the surface of it, that looks like it's a mistake, high release rates, high realized crime, not just predicted crime. But of course, you could say, no, I don't know if you know how this works. You draw a threshold. Maybe this is where judges drew the threshold. Of course, you can't rule that out. So let me show you what we did about that. One of the problems in this machine learning literature is that it sits in its world where there are faces, there are data sets, data unsullied largely by the kind of problems you and I work with. What do we work with? We work with measurement errors, selection biases. You'll notice there's a problem in this data set. I know the labels. I know the presence of face, in this case, committing of crime, for everybody the judge released. I have no idea what happens to the people the judge didn't release. So why in this graph did I point out what we're doing over here? This group that was pretty low risk, but the judge was jailing, about 20% of them. Is the judge screwing up on those people? I can't tell. The judge is deleting the information I would need to compare their predictions. This is important because I think there's a lot of work in this literature that kind of starts with this, goes through graphs like this and said, I managed to predict crime pretty well. Okay, but that doesn't tell us. We want to do some counterfactual exercises. And to do that, we're going to hit the kind of problems that people in this room are very familiar with. So how do we solve this? So it's good that Jeff is here. I'm going to use a trick from Jeff. It turns out that judges are semi-random assigned. In our case, it is just pseudo-random assigned to cases. So what does that mean? That means we've got some judges getting very similar caseloads as other judges, some of which are much more lenient than other judges. Does that make sense to everybody? Now, here's the one thing I can't do. I can't release somebody, but I can always jail people. So I'm going to start with the most lenient judge's caseload. And I'm going to say, let's start with those people. That judge, let's say, releases 90% of people. And I'm going to use the algorithm to decide who the next 10% should be. And I'm going to contract my way down to 80%. And I'm going to say, how much does the lenient judge plus my decision of who the marginal people are compare to what the 80% judge does? Now I've done nothing. I've done a counterfactual, but I'm not making any assumptions about the people who the judge jailed. You may realize that the difference between this and an experiment is my ideal judge is a judge who releases everybody. Now you'll notice this is related to another problem, credit scoring, which I'll come back to later. And in fact, in the early days of credit scoring, companies would in fact give loans unconstrained to a large group of people just so they could get the full spectrum of the data. So let's see what happens when we do that. Here's the most lenient judge. I'm going to move down from that. From the most lenient judge, the next most lenient quintile jails about 6.7% more people and accomplishes about a 10% drop in crime. If the algorithm had decided on that 6.7%, we would have gotten a 17% drop in crime, so about a 75% larger reduction. Or you could have said, why go that far? If you were okay with this drop in crime, why don't we go over to this part of the curve? So I can get you the 6.7% that you're getting right now, the 10% drop in crime, with only 3.5% increase in the jailing rate. So this is a little bit, and these numbers are a little higher than what we typically get, but you can basically have the same level of crimes we have in this example, but jail about half as many people, or drop crime rates about 70%. Now, there's some screws to tighten here. How do you know that this judge isn't some magical good judge, that that's what's doing the work, and we can come back to all that. But the point is, from this type of stuff, by looking at all the other quintiles, you can see there's a potential for huge improvements in this space, because humans here are doing something that is essentially what a machine could help them with. So the essential ingredients here, I think, are we have a pivotal decision based on some sort of prediction. We have people left to predict on their own, which, if behavioral economics has taught us anything, it's kind of it's a tough thing. I mean, how would a judge unqualifyingly beat an algorithm that is able to see 2 million cases? The judge may be able to add information to that algorithm, so I'm not suggesting replacing the judge with this, but surely that information, the 2 million cases, is not something the judge is going to intuit on their own. And in this example, there's data at arm's length. Like, we got this data and we built this tool. And finally, we can compare the human decisions to machine predictions. So what I want to talk about is this category of problems. I actually think there are quite a few of them in finance. So for example, let's start with credit scoring. Credit scoring is this kind of y-hat problem. But of course, it's being solved by industry with a very specific goal in mind. That's not obviously the question that people themselves have in mind. Here's one that makes that point very clear. If you look at home purchases, what's the first question I think most people ask? At least the first financial question. How much home can I afford? That's a y-hat question. At what threshold does someone like me tend to start defaulting or feeling some pain? Again, industry answers this question to some degree, but the question I'm asking is not how much house can I buy before I run risking afoul of the bank's profit bottom line. I'm asking how much house can I buy comfortably. We're starting to get enough data to be able to predict some of these things for people. Here's another sort of consumer finance question. Most people who get unemployed, one of the key things they ask implicitly is, how long will I be unemployed? You need to know that to make lots of decisions, such as, should we sell our house? Should we cut back on consumption? Should we dip into savings? All of these questions are y-hat questions. They have the features of bail, individuals making these decisions. The data is just there. We could build decision aids. There's no reason banks, UI systems, whatever, in improving consumption choices couldn't readily just say to people, here is some information based on the best prediction that we have. So let me conclude. These are the three categories of applications. Let me start by saying I really think finance is one of the massive empirical successes of social science. And I think one reason finance has flourished is it's in part focused on prediction. This whole exercise has taught me something. I thought when I was doing empirical work, I was touching like the data and seeing the real world. And I've kind of realized there's something amazing about prediction, because prediction accuracy is an observable quantity. The reason we can tune is I can say, I predicted this well. That's not a guarantee. Well, you look for yourself. You have this another data. See how well I predicted. It's an observable outcome. Coefficient estimate quality is not an observable outcome. People say, I have an unbiased estimator. I can't verify that empirically. I mean, we can talk it through. Oh, I see what assumptions you made, and hence we have seminars. But there's something beautiful about prediction accuracy. And if you look at finance, that's what made finance really fly. It was, well, you can't predict stock prices. 20 years later, actually, it turns out we can. No, you're lying. Oh, actually, yeah, we can. Because we went and looked at the data. It wasn't disputing that you had some omitted variable bias. It was either predictable or not. I think machine learning offers this advantage to a wide variety of problems. Because as I started, a lot of empirical work, certainly I'll just speak about myself, I relied on a ton of structure reflexively. I decide what variable I'm going to include. I decide in what ways to include them. Like, will I add an interaction? I'm deciding that. There's a lot of structuring of the problem by me. If you look at machine learning, it flourished by moving away from this view. It flourished in sentiment analysis by saying, well, we can't do that. Don't impose an x-ante x-y relationship. Figure out what makes the positive review. And I think that's maybe where I see some of this heading in the more radical sense, besides the three that I described. Maybe this is a way that we can start to let the data speak more, that we can do this in social science as well. I think that structure is valuable without question, that theory is valuable, the things that derive our structure. But, you know, so is the ability to look at data flexibly, sort of, but rigorously, and to discover things. Because sometimes when you look at the data, you discover that some of your bananas are bent the wrong way. All right, thank you very much. So David is very much into Twitter, ever since he saw that tweet. For questions, we'll try something to see if it works. If you have a question, why don't you tweet it with the hashtag, here, I'll put it up here. Here we go. And then that way, oh, I'm putting it up. Don't worry. And so we can, if you tweet that, David can see it. I've set him up so that he should be able to see it. All you have to do is hit. And in the meanwhile, if there are other questions, we can take one of them now while you tweet your questions, actually. This will give us all give me a time to take a drink. Why don't we take this question now, and then are there questions coming, David? Sorry, go ahead.
First, I want to say thank you for a fascinating lecture.
Is that on?
Yeah.
Oh, good. Now
Okay.
it's on. Yeah, yeah.
Thank you for a fascinating lecture on the scope of machine learning in finance. My question has to deal with the asymmetric cause of type 1 and type 2 errors in prediction models. And it's very relevant when it comes to instruments in finance, because the cost of type 1 and type 2 error is very different for stocks versus bonds. So I'm the head of the fixed income research in Alliance Bernstein, and we manage about $500 billion. And we think about this problem a lot. Constantly, we're trying to sort of find better ways of coming up with Y hat. I don't care anything about my B hat. I'm measured by my Y hat all the time. So it is important for us to think about these different approaches. Now, what we struggle with sometimes is the asymmetric cost problem, because if I get a big position wrong in Colombian local bonds, I'm screwed, right?
Yeah.
Totally screwed.
Totally,
But I don't mind missing the apple going from 100 to 500.
Yeah.
So So I think in that context, I think
Let
you
me, yeah,
started
let me
to
talk
touch,
a little bit about that. Yeah,
you
that's-
started to touch on that when you talked about the judges sort
Yeah.
of getting
Yeah.
the.
Yeah, let me talk about that. I think that
Thank you.
let me talk about it narrowly, and then I'll talk about the broader point it illustrates. So narrowly, one way to think about these prediction problems is that once you put it in an econometric framework, it's merely the algorithms taking a loss function. And so those preferences should be embodied in that loss function. Now, let me take, I think, the deeper point here, which is a lot of the errors in this field happen at the mismatch at those handoff points. So for example, the loss function, that's something everybody in this room should be thinking about. Let me explain what I mean. You gave the Colombian bonds example. So I think if you brought in a data science person and say, well, you tell me the loss function, I'll write it down. But it's not as simple as that, because it's not simply the asymmetry. For example, you care about the covariance in some of the positions that you're taking. So the loss itself is a pretty complex loss function. And there's a lot of, for example, you might care about your expected return in a risk-adjusted sense or in a full sense. So as a result, imagine what happens if that risk adjustment is done poorly. Then what the algorithm is actually doing is loading up on a bunch of correlated or tail risk. But for the loss function that it was given, it will look like it's doing very well. This is just by way of saying in corporate finance, we've all learned the Holmstrom-Milgram lesson of don't pay for A while hoping for B. The loss function is central to any machine learning exercise. And that's the kind of thing we've been thinking a lot about, the complexity of that loss function. And in finance, it's far more complex. It's the asymmetry is a good one that you're raising, but so is all this interactive stuff. If I were to describe what I think might be a huge problem, take credit scoring. Right now, I wouldn't surprise me if a lot of the losses that are being put out there in minimizing the credit scoring are insufficiently taking into account the tail risk. Certainly the correlated aggregate macro tail risk. Well, when that's happening, you have a system-wide risk that's creeping into the system through the algorithm. It's not even moral hazard. It's everybody's like, yeah, we're getting these algorithms, they're getting this credit risk. So it's those type of systematic things omitted from the loss. And in general, I would say, we call this omitted payoff bias. It's sort of misspecification of the payoffs can have massive first-order losses, costs in prediction. So let me take a, are you getting the questions?
I'm getting some questions.
Oh, man, you want to?
So there's a
David,
question,
you can pick, yeah.
There's a question about the fragility of prediction, and do you worry about not being able to validate the theory behind prediction? There's also a question about.
Let's do that one.
Okay,
That's
let's do
helpful,
that.
yeah.
Okay.
So I think I have to, this is such a central question. That's not that important. I'm talking, no. I mean, really. You all teach, you know how this works. No. The question is the relationship between prediction and the fragility of prediction, and in particular, how it relates to theory and whether. And I think this is, maybe if I were to unpack the question a little bit, there's a perspective on prediction, which is, wow, predictions can be very fragile because they're atheoretical. Theoretical models can be very robust. And so are we making some mistake? And I think there's a deep challenge here, which I don't know of a polite way of saying it, but maybe so I'll say it impolitely. I don't feel like our theories in social science have been so successful that we should be saying our theories are really good. We don't want to look at a black box. In fact, going back to the risk prediction thing, if I came to whoever it was that was saying this about, let me predict risk, and I said, hey, don't use all your black box Y-hat models. I've got a really good utility model of risk-taking behavior of people and how it aggregates up through the macroeconomy. Use this. It'll be more stable. Now, I understand in writing a paper I could say that, but if it were my money, I'd be like, let's think about this for a little bit. And so that is, I think we don't know enough at this point to score this in social science. We may very well find that our models are actually quite stable out of sample, whatever. But if you look even in the experimental literature where we run experiments, the biggest question is external validity. I ran an experiment in 1998, like Jeff did on Moving to Opportunity. This stuff is really interesting in these 4 or 5 cities. How well does it generalize to other populations? How well does it generalize to 2016? These are questions that are hard because we don't know how well things generalize to other data sets, and we don't live in a field where we've got theory that say to us it's going to generalize. And so I don't know whether predictions themselves aren't more robust because they pick up a lot of variables that we wouldn't know to put in, that then they may be able to do a better job. So that's my very general point. The specific point I'd make is it's another interface point. I think in machine learning, people don't think much about standard errors. So they don't realize, for example, in finance, one of the things you have to think about is very carefully about generalization. So what is the out-of-sample thing that you're testing on? In finance, it's the next year. You can't really say, I generalized, I did a subsample as the holdout. You don't want to do a subsample as the holdout. You want to do it in the next year. And what's your standard error? It's actually the year-by-year term. So you need 5 years so you can pin that down. So there is a bunch of, I think, stability issues around standard errors. But at the deeper level, I think this is an answer. Should we take another one? Or?
I guess related to that is a question about using machine learning for predicting returns.
Yeah.
And do you think it's an acceptable academic practice to do that?
Wow. I think the time I'm telling people what's acceptable is, I'll be honest with you guys, I don't understand to some degree how much this stuff has penetrated into the private sector. So let's just take the extreme view. It's all penetrated. It's kind of an extreme view, which seems to me can't be right, because we've seen a lot of people in finance do work and then make a lot of money in the past. So, but even in that extreme view, there is a huge comparative advantage, I think, that we provide, which is in predictability, it's often interesting if it turns out categories of variables provide signal that we don't know they provide. And so if it's not simply chasing returns predictability, but decomposing the returns predictability we have, or kinds of variables that might have returns predictability, so I'll give the best example of this. I feel like there's a huge behavioral finance literature in investor sentiment. And sentiment is this funny thing because it's like this hidden variable that can do things and move, and we've been talking about this for a while. It is not implausible to say in this returns predictability thing, can I use the language data, the message board data, the Twitter data, and certainly a lot of people are dancing around this issue, not for the purposes of I'm going to predict the stock market better than somebody else, but for purposes of trying to put structure on sentiment. Is sentiment unidimensional? Is it two-dimensional? Does sentiment differentially affect certain stocks versus other stocks? So I do think that there's a way, even if you're not in the business of just trying to predict returns for purposes of making money, there's a lot that can be understood, because I think that 40 years ago, this was, asset pricing was very straightforward. Now we've brought some elements into the room, like sentiment, which are pretty wide open and which I don't think we're going to understand just by looking at price and volume data. I think if we're going to look at sentiment, we're going to need something else. And there are equivalent things in corporate finance. The people are talking about overconfidence. A lot of concepts have now worked their way into finance, which I think are best understood through some of these other data that now we're starting to open up. Should we do one more and then?
Sure. So the question about the research agenda of Athey and Imbens, which combines causal inference with machine learning.
So this is a question about Athey and Imbens, who combine causal inference and machine learning. So this stuff is very interesting. There's a big and growing literature. I think the economists most prominent on this are Athey and Imbens, but Viktor Chernozhikov is also doing a lot of interesting work in this area. And I think it's very interesting because once you have an identification assumption, like I've got an experiment, then machine learning might be able to help you do other parts of it. So say I ran an experiment, and now I want to look at heterogeneous treatment effects. Well, heterogeneous treatment effects is a y-hat problem. And here's what I mean. If I said the treatment effect is higher for older people, that's not a causal statement. I'm not saying if I made someone older, the treatment effect would be higher. I'm just saying that's what it looks like. That's pure prediction. And so they have one paper that does that very nicely, and Viktor Chernozhikov and co-authors have a set of papers that start to work in this area. And I think you can kind of understand that even in causal inference, like IV had a prediction component, even experimental analysis of treatment effects. Jan and Jens Ludwig, a co-author of mine, have a paper where they show how multiple outcomes testing turns out to be, in experiments, turns out to be another y-hat problem. So there are a lot of these y-hat problems that sit in the causal inference world, and they sit there, which is, once you make the identification assumption, a lot of what you tend to do is actually prediction-like. So let me stop there. Is that good? Great. Great. Thank you all.
Thank you.
Thank you so much.